Hello my student, this is Dr. Sirme. First of all, I want to thank you people for subscribing to this channel, and kindly, if you've not subscribed, kindly do it for me. Today I want to take you through the chemistry of ammonia. The chemistry of ammonia. And previously we've done the chemistry of sulfuric acid, and of course among other very important content there. Kindly subscribe before even we proceed. Thank you. This is the chemistry of ammonia. As you can see there, the formula NH3. NH3. And basically the areas that I'm going to cover, I will talk about occurrence of ammonia. I'll talk about the laboratory preparation of ammonia. I'll go through some physical and chemical properties of ammonia, the fountain experiment for ammonia, then the large-scale manufacture of ammonia, a process called Haber process. Then I go through some uses of ammonia, and finally I will talk about some nitrogenous fertilizers. The introduction part. Ammonia is a compound of nitrogen and hydrogen. As you can see the formula there. Actually, in short, we can say it is a hydride of nitrogen. Considering that nitrogen is atomic number 7, electron configuration 2,5. Hydrogen is atomic number 1. So electron arrangement 1. So with that, both of these elements are nonmetals. So they will bond covalently by sharing of electrons. Like you can see there, the bonding in ammonia, there are 5 electrons in the outermost energy level of ammonia, as you can see, the dots. Then 3 electrons pairs with 1 electron from hydrogen to form 3 covalent bonds. So there are 3 covalent bonds, you can see the shared electrons. Then there is a lone pair of electrons that is not used in bonding, and that is the bonding in ammonia molecule. Okay, next we can talk about occurrence, how ammonia occur in nature. Naturally, ammonia will occur in urine of mammals, even in excretion of birds, and that's why we say, for instance, for those who are good in farming, the poultry manure, it's very much rich in nitrogenous content or nitrogen content. It has too much of ammonium compound in it. And ammonia can also be formed in kidneys of human beings. And the next laboratory preparation of dry ammonia. It is dry ammonia. Reagent that we need select lime, that is calcium hydroxide. Yep, you can see the formula. You need ammonium chloride. You can see the formula there. Of course, you need quick lime, that is calcium oxide, solid calcium oxide that will act as a drying agent. Now the setup is as I've given there. You can see a round bottomed flask with a mixture of calcium hydroxide and ammonium chloride, and it is heated. Look at the flask. It is in a slanting manner. That one you should know why. Then of course the gas is taken to the drying tower, where the calcium oxide, quick lime, is fed there. Then of course you can see the gas is collected by downward, this is a upward delivery. Yes, upward delivery, or rather it is called downward displacement of air. Okay, that one is still another setup for the same, but the first boiling tube here should be in a slanting manner. We are going to see as to why that is done. Okay, even the drying agent, we're going to ascertain why is calcium oxide the best. Why is ammonia collected by this method, as we can see later. The chemical reaction taking place, ammonium chloride reacting with calcium hydroxide, yes, calcium oxide is formed, and water, and of course the ammonia gas. Maybe you ask yourself, have you ever come across this equation? That's a question you should ask yourself. Where exactly did you come across it? This one was covered in Solvay process. The main equation for the regeneration of ammonia in Solvay process is exactly this one. Now, the ionic equation, if you may like this one, Yes, the hydroxyl reacting with ammonium to form water and the ammonia gas. Otherwise, if we can prefer to use another base instead of calcium hydroxide, sodium hydroxide will also do, and the equation is as I have given you there. Even potassium hydroxide will work the same. You can see the chemical equations there. Generally, what is happening? Ammonia is more volatile, just like we said with sulfuric acid in my previous upload video there. Ammonia is a more volatile base, hence it can easily be displaced by the less volatile bases like sodium hydroxide and potassium hydroxide or calcium hydroxide. That is a property that will apply to both acids or bases. If we proceed, there goes a question: why is the round bottomed flask placed in a slanting manner? That is a question that I want us to answer. Calcium oxide is used as a drying agent. Explain why concentrated sulfuric acid or anhydrous calcium chloride cannot or are not suitable drying agent for ammonia. Good. These two questions, expect them. Expect this question in any exam because it's very key to understand. Now the answers. The reason why the round bottomed flask is in a slanting manner, it's basically what I've given you to prevent water from condensing inside the flask. Okay, if it condenses and it will run back, and of course that will lead to the breakage of the hot flask. So that is the reason for that. Number two, why concentrated sulfuric acid and calcium chloride anhydrous, they are not good drying agent for ammonia. Both of them, they will react with ammonia, and of course if the drying agent reacts with the gas that you're preparing, of course you not get the gas. Yes, so as you can see, if it is sulfuric acid, it will react with ammonia gas to form ammonium sulfate. If it is calcium chloride, it reacts with ammonia, as I've given in that equation, to form a complex of ammonia, as you can see there. So that one, it's a question that my student, you should get it and get it very well. Moving on, the physical properties of ammonia. Ammonia is a colorless gas. It has a characteristic pungent smell. That is pungent and choking smell. Choking means it can temporarily interfere with your breathing. Pungent means very, very sharp. Actually, it has a smell of urine. It is less dense than air. It's a very light gas and hence is collected by upward delivery. Otherwise, it is called the downward displacement of air. It is not. It does not support combustion. Yes, it does not support combustion. It is almost incombustible. Does not burn. Then going on, it condenses at negative 34 degrees Celsius. So it is a gas. At room temperature, ammonia is a gas. It is highly soluble in water. Actually, it is the most soluble gas that we study in high school. Then it's an alkaline gas. Yep, it is actually again the only known alkaline gas that we cover in high school. If you subject it to a moist red litmus paper, it will go blue. And just that point, as I've said, it is the only alkaline gas covered in high school. Now, how do you confirm the presence of ammonia? Good. One way to confirm the presence of ammonia is the use of a litmus paper. You can use the red and blue litmus paper. Then you observe. So if you subject moist red litmus paper and a blue one to a gas jar containing ammonia, the observation will be the blue litmus paper remains blue. It is alkaline. The red litmus paper will go blue, as you can see here. Ammonia is an alkaline gas, and again, it's the only alkaline gas that we cover in high school. So that is a distinctive feature that can help you distinguish ammonia from other gases. Confirmatory test again using hydrogen chloride gas. You can dip a glass rod in concentrated HCl, then you bring it in contact or at the mouth of a gas jar containing ammonia. Actually, we usually say a white cloud or some white fumes will be observed. As you can see the equation there, ammonia will react with the HCl to form ammonium chloride. That is the white substance that will be formed. Again, this can be a confirmatory test for ammonia. Moving on, how do you prepare aqueous ammonia? Aqueous ammonia. Okay, the procedure, you need a filter funnel and you fix a delivery tube to the filter funnel. Then you connect, of course, the delivery tube to the source of the dry ammonia. Then you have a trough containing some water and invert, to the next point, invert the filter funnel on the water in the trough. And the setup, as you can see, look at that. This is very important because the question will always be asked, why do we use the funnel, the filter funnel? Good, and that one we're going to explain shortly. Sometimes you can leave a very small space between the filter funnel and the water just to ensure that the atmospheric pressure just balances in and out to avoid the creation of a suction or a vacuum that will suck in the water. And that is basically the discussion. Ammonia is very soluble in water. Yep, a drop of water will just dissolve large amount or volume of the gas. So the filter funnel there is to increase the surface area. And once you increase the surface area, the ammonia gas will be dissolving on a very bigger surface area. So there will be no suction that is being created or vacuum. And the surface area, when it is increased, this prevents sucking back of water. This is a question that was there in just some few years in KCSE. The solution that will be formed will be ammonium hydroxide. Sometimes you call it aqueous ammonia. Sometimes you call it ammonia solution. Sometimes ammonium hydroxide. So that is that. Note this, other gases that are very soluble in water, they can be dissolved using the same way, using a filter funnel. For instance, sulfur oxide, hydrogen chloride, another very soluble gases, you should use a filter funnel when you're preparing their solution. Okay, these gases are very soluble as well. A fountain experiment. I know my student, you all know what is a fountain. Maybe you've been to these big cities, and of course you see the recreational monuments they make. Okay, those are called fountains. So I'm not going to explain any further about the fountains. I am assuming that my student, you know what is a fountain. Now the procedure. You need to fill a round bottomed flask with dry ammonia. Then you fix a cork, and of course the cork should have a delivery tube with, of course, a very small opening there, and at the bottom a tap. There should be a tap. Okay, then you place some water in a trough. Yes, then you add universal indicator or litmus solution or phenolphthalein, whichever one you prefer, maybe 3 or 4 5 drops there. Then you lower, yes, I'm going to show you the setup next, but you lower the what we call now the outer part of the delivery tube that has the tap into the water, and slightly open the tap to allow just a drop of water into the flask. Then fully open the tap. Yes, I know the procedure is quite detailed, but it is very simple. Look at that. The setup. Let me first of all show the setup. Yes, the setup. Look at it. What I'm just saying is this is a round bottom flask. You have a delivery tube here with a tap. You can prefer to use a dropping fan, but that is a teat pipette. Yes, a teat pipette or a dropper, just to introduce the drop of water, or use the tap like I have described. You open the tap slightly, let the water in, then open it. A fountain will be formed here. Water will splash out from this point here, and a fountain will be formed. What exactly is being happening here, or it's happening here? When the tap is fully open, yeah, remember the first opening was to introduce a drop. The drop will dissolve all the gas that was inside, and a vacuum is created. So when you fully open the tap, the blue fountain, in case you're using litmus solution or you're using universal indicator, a blue fountain will be formed. Okay, in case you're using phenolphthalein, you're going to observe a pink, okay, a pink fountain there. Remember, ammonia is alkaline, so your the color of the indicator will just be dictated by that fact that ammonia is alkaline. So blue in universal indicator or litmus solution, pink if you're working with phenolphthalein. Okay, that is an experiment you can just try. Even for sulfur full oxide or HCl gas, you can have it that. Well, that is all that I've discussed. Ammonia is very soluble in water. When a drop is introduced, all the gas in it dissolves. If you open the taps again, then a vacuum that was created, atmospheric pressure from outside pushes, now pushes, yes, it is pushes water in to occupy that vacuum, and a fountain is created. Other gases, like I've said, that can form fountain, sulfur full oxide, HCl gas, because they are very soluble. If you use phenolphthalein for this case, the fountain will be colorless. Yes, because both of these gases are acidic. Sulfur full oxide and HCl gas are acidic. Chemical properties of ammonia. Very fast reaction with water, reaction with acids, that is combustion. Yes, of ammonia when it is in air is enriched with oxygen. Then reaction with air again in presence of a platinum or nichrome wire. Then reducing property. Then how aqueous ammonia react with metal ions. We go to the first reaction, reaction with water. Ammonia dissolves in water to form aqueous ammonia, and this one we said ammonia is a very, very, very soluble gas. As you can see, ammonia, you can put it in water, you get aqueous ammonia. Sometimes very little of ammonia, aqueous ammonia, will dissolve in water, to form ammonium hydroxide. As you can see there, the equation there. Looking at that, we are talking of very little of ammonia dissolving, and that makes ammonia solution a very weak base. Unlike the sodium hydroxide or potassium hydroxide, which will dissolve completely, this one, very little of ammonia will be in aqueous solution. So it will be, most of it will be in molecular form, that is ammonium hydroxide, and that makes it a very weak base. Going on, the bonding in ammonium, because what is formed is called ammonium molecule, ammonium ion, sorry. Looking at this, initially we had a lone pair of electrons here. So the water, if you put ammonia in water, that's very little ammonia in water, you're going to have a hydrogen ion from water bonding with the lone pair here. This bond is called the coordinate bond or the dative covalent, because the hydrogen ion atom here or ion comes with 0 electrons. So it bonds with the electrons from the ammonia molecule. And of course the rest are, of course, the covalent bonds. You can see the charge, yes, it has a positive one. That is the bonding in ammonium. That is called ammonium ion or ammonium radical. Reaction with acids, very fast. Ammonia is a base. Acids, of course the acids here. The reaction between an acid and a base is called a neutralization reaction. And the neutralization reaction in this case will give you ammonium salts and water. So some chemical reactions, as you can see, all of them, yep. Ammonium hydroxide reacting with sulfuric acid, you get ammonium sulfate and water. If it is HCl, you get ammonium chloride, ammonium nitrate with nitric acid, and ammonium phosphate in case you're working with phosphoric acid here. These are the chemical reaction, neutralization reaction. In case we're talking about ammonia in dry form, that is dry ammonia, it will only, if it reacts with an acid, it will only produce a salt as the only product. That's ammonium salt. The chemical reactions, as you can see, yep, we are talking about ammonia gas reacting with the acid. You get ammonium salt as the only one. Okay, you can just go through those equations there. Moving on, combustion of ammonia in air that is enriched with oxygen. Remember, we said ammonia is almost incombustible, but you can have it reacting or burning in presence of too much of oxygen. That is oxygen, the air that is enriched with a lot of oxygen. And for example, as you can see, it can ignite. It can ignite in presence of too much of oxygen. A yellow-green flame will be produced and a colorless gas. The discussion for that: ammonia will burn with that yellow-green flame in air that is enriched in oxygen. Nitrogen gas and steam are formed. The equation is as it is there. That is the first one, because you should know when ammonia is burning in presence of oxygen, yes, that of air that is enriched with oxygen, and when it is burning in presence of a catalyst. Okay, so that is the first one. Get here and get it well. Nitrogen and steam, those are the product. When you're burning ammonia in oxygen, that is excess of oxygen. If we are talking about ammonia burning in air in presence of a catalyst, in this case it will be platinum or a nichrome wire. My student can also check whether copper can also be used as a catalyst in this one. Okay, when you place a platinum or nichrome wire in a concentrated ammonia solution, actually above, not in it, you just place it above. What will be the observation? The wire will continue to glow. That is red hot. What exactly will be happening? And of course the brown fumes will be observed. The discussion for that: ammonia will react with oxygen on the surface of these wires, because the wires will be acting as a catalyst. The platinum or nichrome wire will be acting as a catalyst, and of course the reaction will be highly exothermic. Yes, if we can discuss further for this one, the heat produced enables the wire to continue to glow. Ammonia is oxidized to nitrogen 2 and water. In the other case, remember we said, if you can go back, we talked about ammonia burning in excess of oxygen to give us nitrogen and steam. But for this one, we are talking about ammonia burning in oxygen in presence of a platinum catalyst to give us nitrogen to oxide and water. That's the difference. The platinum, of course, and nichrome behaves as a catalyst for that reaction. Do not forget that. If you think about nitrogen 2 oxide, a very unstable gas that can easily be oxidized further to nitrogen 4 oxide, and that's what exactly happens, because nitrogen 2 oxide is a colorless gas, so you cannot be able to observe it. But nitrogen 4 oxide, you're going to observe it as the brown solid there, the brown gas there, as you can see. The chemical equation for that, you can see. And even when nitrogen 2 oxide is oxidized further, yes, you can see what is happening. My student, kindly master the equations. Master the equations, and be sure in any normal and very serious and standard exam, the questions will always be there. How to balance, I've taught you even before. The reducing properties of ammonia. It's a good reducing agent. The experiment we're doing there, we are passing ammonia over heated copper 2 oxide. The setup, as you can see there, you have the tube K, that is the combustion tube, dry ammonia being directed in, copper 2 oxide inside the combustion tube that is heated. The content of the product that comes out goes through a U-tube that is immersed in ice cold water. A liquid there, L, is formed. The rest of the gas comes out as nitrogen there, and it's collected over water. That is the setup. You can just study it. Stop the video and try to study that setup. Then we do the observation inside the combustion tube. The black copper 2 oxide, remember copper 2 oxide is black, it will change to brown. Droplets of a colorless liquid, they are formed on the cooler part of the combustion tube. That is still in the combustion tube. If we can talk about the U-tube, what exactly is happening inside the U-tube? A colorless liquid is formed. Inside the gas jar, a colorless gas is produced. Those observations, you can look at them again and even go back to the diagram. Yes, go back to the setup, try to see what you say. Here we've talked of copper 2 oxide changing from black to brown. Hapa tumesema there will be a colorless liquid. Over here, a colorless gas. So that is something you can revisit and revisit and revisit. What exactly is happening? Dry ammonia inside the combustion tube reduces copper 2 oxide and copper metal, that's now the brown solids, they are formed. Water, that's a colorless liquid, and nitrogen gas are also produced. You can see the chemical equation there. The black solid here, yes, the black solid here changing to brown, that is copper metal. Then nitrogen gas, a colorless liquid, water, all it is formed there. If you ask what is the use of the ice cold water, it is just to condense the steam to form this water. Other oxides that can be reduced by ammonia, lead 2 oxide, iron 2 oxide, they can be used instead of copper. And of course you can see the equations that are taking place there. Yep. Yeah, if it is for lead 2 oxide, you can see it will change from orange when cold, brown when hot, to gray. That is lead metal will be formed. Iron, yeah, will change from green, iron 2 oxide, from green to gray. The equations, they are there. Other metal oxides that are lower in the reactivity series, they can behave almost the same. That is very good concept there. So how do you confirm the presence of water? Because they will tell you how do you confirm that the colorless liquid you've seen in the YouTube is water. That is Form 1 work. Either we use anhydrous copper 2 sulfate, or we use the anhydrous cobalt 2 chloride. With that, we can move on. Yeah, what exactly will happen if you are using copper 2 sulfate anhydrous? It will change from white to blue. That one. And if you are using cobalt 2 chloride, the first one was sulfate, the other one is anhydrous cobalt 2 chloride, then it will change from blue to pink. And this is the confirmatory test for water. And my student, get it well. If they are talking of physical properties of how you can confirm the presence of water, talk about the density of water, 1 gram per cubic centimeters. Talk about the boiling point at sea level, 100 degrees Celsius, and then the freezing point, 0 degrees Celsius. Those are just but the physical test for water. But confirmatory tests, chemical one, it's what I've described here. If I want to confirm the presence of nitrogen, the colorless gas, nitrogen, we usually say it gives negative results to all common methods of testing the presence of other gases. For example, it will have no effect on blue or red litmus paper. It will not support combustion. It's not combustible either. It has no effect on lime water, like for CO2. It cannot produce a pop sound, etc., etc. So that is that. Maybe a revision question here. Name 2 other gases that can behave the same way as ammonia in reducing metal oxides lower in the reactivity series. The answer, hydrogen gas. That is Form 1 work. Water and hydrogen. Hydrogen has a reducing property. Carbon 2 oxide, Form 2 work. It has a reducing property. My student, master and get that very well. Moving on, if you're talking about ammonia solution reacting with metal ions in solution, this is a concept that I've done in one of the videos I did, but I can simply discuss what it's entailed here. Ammonia can precipitate some, not all, it can precipitate some metal ions from their solution in form of hydroxide. And ammonia being a weak acid, of course, a weak base, it will not, it's a weak, I think you can get that correction. Ammonia being a weak base, it does not precipitate the highly soluble hydroxide. So for that, we can have a table that do summarize. This table is very important. When you're adding few drops of ammonia and excess of ammonia, what exactly happens to a solution containing metal ions? Like I've listed down 9 of them, yes, here, 9 of them. If it is with magnesium, few drops, white precipitate is formed. In excess, the white precipitate is insoluble. With that, you can see some similarity with lead 2 ions. White precipitate that is insoluble. Barium ion, it is aluminium. Aluminium again, white precipitate insoluble. If it is with the barium and calcium, The two will have no precipitate. Ammonia cannot be able to precipitate the calcium or barium ion. That one you should get. Some other ions that have similar behavior, zinc and copper. Zinc ions, white precipitate. White precipitate dissolves, okay? With copper 2 ions, or pale blue precipitate, the pale blue precipitate dissolves. So the two will dissolve. A very good chemistry here that you should be able to know, because it's very important in paper 3. Okay, maybe some ionic equations. This one I won't say much of what is happening. We have talked of white precipitate, green precipitate, brown precipitate, and so forth. You can see basically what is happening there. What exactly is happening. The ionic equation, especially when you add few drops. And maybe we can only concentrate with copper and zinc that forms a precipitate that is soluble. This one we call them complex ions. Basically what happens is that the few drops added, you form a hydroxide. If you continue adding the hydroxide, the amphoteric hydroxide continues to dissolve in ammonia to form a complex. Like you can see the zinc hydroxide, the white precipitate, copper 2 hydroxide, the pale blue precipitate, they will dissolve in aqueous ammonia, and they will form, like with the zinc, you can see the complex tetraamine zinc ion. You can see there the complex with a charge of positive 2, that one you can tell. Okay, with the copper 2 hydroxide, the pale blue precipitate dissolves in aqueous ammonia excess. Tetraamine copper 2 ions are formed, the deep blue solution there. Good. I hope that one, my student, you are able to see. You can draw even those complex ions. Qualitative analysis using ammonia solution. And this one I've just said, the ammonia solution, it is very important when it comes to the analysis of cations in qualitative analysis. And they are used together with sodium hydroxide. Sodium hydroxide is used for the preliminary, ammonia solution is used for the confirmatory, and other salts, other soluble salts. For instance, you can have soluble sulfate, soluble carbonate, selectively soluble chloride, soluble iodides. They can also help in finalizing or identifying the final cations that are present in a sample. So kindly, what I'll urge you, my student, I have 3 uploads that I did for sodium hydroxide alone, for aqueous ammonia alone, and also for the both of them combined, a sample question. So check in my videos kindly, and just learn more about that. Good. We go on now to a very important process, the Haber process. And as far as Dr. Sirme is concerned, this is my 4th. This is my 4th industrial process that I have covered. So far, if you check, you can see I've covered the Solvay process for the manufacture of sodium carbonate. I've also covered the Frach process when I was revising KCSE 2021 paper 2. The Frach process for the extraction of sulfur, that one my student have done for you. I've done just the other day contact process. And now we're doing the 4th one, the Haber process, by a German scientist called Haber. Now the raw materials that I need nitrogen. This one I can obtain it from a fractional distillation of liquefied air. That is an industrial process in form 1. I can also get hydrogen. Several methods that I can get hydrogen. Remember the 2 raw materials. I need nitrogen, I need hydrogen, and of course water. I can get hydrogen from water gas. That is carbon that is burnt or mixed with a steam, and you get CO and hydrogen gas. So you can get hydrogen gas in that way. I can pass natural gas, that's methane, through steam, and still I can get CO and hydrogen gas. My aim is to just get that hydrogen. Later I can remove the CO and use the hydrogen. Or rather I can do the cracking of long-chained alkanes. Good. The process itself, it has 5 compartments. Like the other one we say with contact process 6. The other one for Solvay, yes, we say it has 7. But this one you can get there 6. The gas purifier, the compressor, the heat exchanger, the catalytic chamber or converter, and then the condenser. They are just 5. Yes, 5. For Haber process, 5 compartments, and that's all we're going to go through. The first one, we talk about the gas purifier. Nitrogen and gas, that is nitrogen and hydrogen, they are mixed in the ratio of 3:1. That is hydrogen and nitrogen, 3:1 in that order. Then they are passed through gas purifier. The method that we use there, like we did before, we use a method called dust precipitation. By dust precipitation, we remove the dust, and of course other chemicals, be it carbon monoxide, you pass through sodium hydroxide, yes, oxygen, you remove it, you can pass it over heated copper, etc., etc. So these impurities, why are we removing them? The very same reason we had before. Impurities will poison the catalyst, so we need to get rid of them. In the compressor and the heat exchanger, the pressure in the compressor is 200 to 250 atmospheres. And what exactly will happen? The hydrogen-nitrogen mixture will liquefy. It will become a liquid. And then the liquefied mixture of hydrogen and nitrogen, it is passed through a heat exchanger. Temperature of 400 to 500 there, or 450 there in the heat exchanger. I hope that one you have been able to see that. The two. We move on. Catalytic chamber. What exactly happens? The hot, remember now it is the mixture of hydrogen and nitrogen is hot and compressed. It is passed through a finely divided ion catalyst that is promoted. Actually, some people say it is impregnated with aluminum oxide or potassium oxide. Remember, these are called promoters. The promoters will increase the efficiency of the catalyst. Yeah, they increase the surface area and the efficiency of the catalyst. The chemical equation that is taking place, you can see nitrogen reacting with 3 moles of hydrogen in the presence of iron to get ammonia. A very exothermic process there. Actually, that is it. The exothermic nature of this process is very important because that heat can be used now to preheat others. It can be reabsorbed, and actually once you heat, you don't need to come back and heat. The heat sustain, the reaction sustains itself is in terms of energy or heat. The cooling, that is exactly what happens. Once you heat the mixture and they react, you take the hot gaseous mixture back to the heat exchanger. And why are you taking that? For the heat to be reabsorbed. And when that is reabsorbed, okay, it can be reused. This makes the process economical. Remember, this is an industrial process. An industrial process need to minimize on the cost of production. And cost of production, for instance, it includes the amount of money used to maybe pay for the electricity that is going to heat these gases. Condenser. Ammonia is liquefied in the condenser and is stored. Basically, as simple as that. The unreacted gases are recycled all the way back to the compressor. Again, to do what? To minimize on the wastage. The cost of production should be lower if the wastage are minimized for the industrial process. Good. If we can talk about the optimum condition, the reaction between nitrogen and hydrogen to form ammonia is reversible. Yes, it's a reversible process, you can see, and it's exothermic actually. So we can borrow some idea from Richeteria's principle and see what exactly happens if we change some conditions here. Okay, the forward reaction is exothermic, and that tells you if we want to obtain high yield of ammonia, we are not going to we can only obtain it at low temperature because the forward reaction is exothermic. And if that process is exothermic, it means you cannot, if you heat, you discourage the forward reaction. You are encouraging the backward reaction. And again, if we borrow again from Richeteria's principle, high pressure. High pressure. What does high pressure mean? It means the reaction will go to the side with less molecule. Yes, at high pressure, more ammonia will be produced. However, what are the challenges of having low temperature and high pressure? What exactly are the challenges? There they are. At low temperature, yes, the favorable for formation of ammonia, actually the reaction will be too slow. You take a lot of time to generate some a sufficient amount of nitrogen. Not nitrogen, but ammonia. At very high pressure, you need a lot of money to buy those pumps that will maintain those very high pressure. So the cost of production will still be high. So to provide a higher yield, we need to choose some optimum conditions. What are optimum conditions? The conditions that will give us the highest yield or production with the minimal cost. And for this one, temperature should be 500 degrees Celsius, pressure should be 200 atmosphere, yep, and of course we use the catalyst. These are the combinations that we can refer to as optimum for Haber process. Now basically we can go through that flow chart. Yep, the flow chart, you can have nitrogen from fractional distillation, we have hydrogen from cracking or the other means. We purify them in the purifier, we take them to a compressor, 200 to 500 atmosphere, yep. Heat exchanger, 400 to 500, yes, for last time. Then we take it to a catalytic chamber, ion, that is promoted by these two, okay? You can see any of these. Taken back to the heat exchanger for absorption of the heat. Then the ammonia that comes out is taken to the condenser. It is taken to a condenser. It is condensed to liquid ammonia, yes, packed and into cylinders, ready for sale on transportation, and reacted gases back to the compressor. That process, my student, is easy to get it. Revise it, get it, and get it well. Yep, even that one is the same. The same version of that Haber process. Air getting nitrogen, hydrogen comes from cracking of alkanes. All the way you purify, compress them, yes, you heat them, take them to a catalytic chamber, then back 10% ammonia, you can see it produced, then taken back to the heat exchanger for cooling, condensed by adding water. Actually not even adding water. Here we don't even add water. We compress. We just not compress, but we condense, and we get liquid ammonia. We move on. Uses of ammonia. Good. Ammonia can be used to make nitrogenous fertilizers. Ammonia can be used to make to manufacture nitric 5 acid. Ostrad process. I think that's where we're going next. Yep. A refrigerant. It's good for refrigeration. It can be used in softening of hard water. Solvay process. Yeah, manufacture of sodium carbonate. Yep, you can have the removal of grease and stain from fabric. You can have the manufacture of hydrazine. That one, it's a mixture that is used to make rocket fuel. Those are just but few, but they are good for you. I can see the 7 uses there. Good. Yep, even if you like it in that format, you can see. It can be used to manufacture a number of things. It can be used to manufacture a number of things, as you can see there. Okay. It can be used to soften water here. Yeah, degreasing agent, the refrigeration, etc., etc. Moving on, examples of nitrogenous fertilizers. Ammonium sulfate. You can see the formula, the molar mass. You can see the content mass of nitrogen in 1 mole of the fertilizer. The calculation of percentage nitrogen, you can see 21.2121% there. Ammonium phosphate, yep, a salt, that is a salt, other is called a fertilizer that is rich in nitrogen and phosphorus. You can see the molecular mass, you can see the content of nitrogen, the calculation of nitrogen content, 28.1879% there. Other examples, ammonium nitrate. Good, you can see the formula, the molecular mass, then the nitrogen content in it, the percentage nitrogen there, and yes, nitrogen 35. Another fertilizer, urea, that is formed by passing carbon oxide through ammonia solution. Remember, nitrogen, that's ammonia, is alkaline, carbon oxide is acidic. So you can see the reaction forming, a salt is formed there called urea. Good. The percentage nitrogen in it, actually you can see there the calculation. Good. We have I hope that you've been able to see. Good. The next one is calcium ammonium nitrate, CAN. This is a mixture of ammonium nitrate and calcium nitrate. Good. The percentage nitrogen is 27, and those are just but 5 examples of nitrogenous fertilizers. Fertilizers are very important when it comes to farming. Agricultural production cannot go on without fertilizers, and nitrogen is very essential. That's why we are studying nitrogenous fertilizers. They are very, very important. Factors to consider when you're selecting a fertilizer for use, depending on the plant, the crop you're growing. Maybe you can talk of nitrogen content, like the nitrogenous fertilizers. How much of the nitrogen is present in that fertilizer, or the solubility. That's why you select, is it a top dressing, is it a direct planting fertilizer, etc., etc. Maybe you can also think about other elements that are present in the fertilizer. For example, the phosphorus. That's why, for example, ammonium phosphate can be more advantageous. It has nitrogen, it has phosphorus. But okay, after taking you through the chemistry of ammonia, here are some revision questions good for you. Maybe the question will repeat themselves somehow, or some of the questions will be very similar. At the same time, I want to urge you, in case you don't get the answer, because generally I'll not give the answers, so you can refer the video that I've just given you. That is question 1, catalytic oxidation of ammonia. Then you write the equation for the reaction taking place, why the nichrome or wire should be hot. Then Roman 3, as you can see there. Then you have question 2, again, catalytic oxidation of ammonia. You identify the metal M, yes, 2 observation in the conical flask. Roman, that is question 3 there. You can see an incomplete setup for preparation of ammonia. Then 2 alkali that can be used in the experiment. You write the equation. Question 4, you can see question 4 there. Well, just go through that. It's a qualitative analysis of metal ions using ammonia, and you can see the question. Then question 5, Haber process, nitrogen and hydrogen. They can be reacted in presence of finely divided ion catalyst. Why should the catalyst be finely divided? Good. Part B, you can see a question that is connecting ammonia with mole concept. Then you have question 6, again, preparation of a gas there. You need solid E and calcium hydroxide, and then ammonia is produced, then pass through aluminium sulfate F, that is a solid F is produced. You identify E and F, and question there. Question 7, you can see, again, a qualitative analysis reaction there. So you need to just follow the question and answer part A, B, and C. Remember, all these are short structured questions. Even question 8, yes, it is starting with the dilute nitric acid. Then follow the question, identify anions and cations present in the green solid, etc. And question 9 there, yes, again, a qualitative analysis question using aqueous ammonia. Number 10, you can see number 10, condition necessary for Haber process. Part B, you can go through it again. Okay. Then question 11, qualitative, this is oxidation reduction process of copper 2 oxide using ammonia. Just go through that question and attempt it. Question number 12, you can see that generally this one is not for ammonia, but remember, nitrogen, it's very much required in Haber process. So this one is for the isolation of nitrogen from the air. But it's a good question. You can also go through it. Number 12 there. Number 13, yes, number 13, you have an incomplete setup again. You're supposed to complete it. And of course, you write the question. Number 14, maybe the last short structured question, the formation of aqueous ammonia. Yes, you can see the funnel, the inverted funnel. Why the inverted funnel? Then what will happen if you dip the delivery tube directly? Observation that are made if a litmus paper is placed into the solution. Again, you can have long structured questions, mainly some questions that can appear in a paper too. Like, look at that one. This is a flow chart. Yes, first of all, you starting with air, nitrogen, and oxygen is obtained. Then Haber process, you go to B all the way. All that you're supposed to do, study the flow chart, then attempt the questions. Like this one, just pause the video, attempt the questions. And as you can see in this one, you can have a flow chart that combines several processes. Like this one combines Haber process and contact process. So kindly study it. Yes, as you can see, it continues there. Yes, part D, E, F, and G are very nice, long, structured question that you can study, and it will help you cover quite a big area. Going on to number 16, you can see number 16, you're starting somewhere with aqueous, sodium hydroxide in a boiling tube, then the content out going through hot iron powder, all the way you have solid Q in a cylinder there. Again, it's for the isolation of nitrogen gas from the air. So you name solid Q, purpose of sodium hydroxide, and this question, etc. You can see Roman 3, Roman 4, and even Roman 5 there. That's Roman 5. This question can help you, revise even other areas that are not necessarily under ammonia. Question number 17. You can see a flowchart again, a long structured question for Haber process. You start with the Haber process that is connected to Ostward's process. Just like I've said, you can have a process like Haber process that is connected to another process, like in this case, Ostward's process for the preparation of nitric 5 acid. Then, of course, the questions. You can go through the question A, B, C, D, E, F, and G. A good question there. In case maybe you're not able to answer the questions, you refer to the video that I've just given you. Another long structured question number 18, study the flowchart, then answer the question. As you can see this one, you're starting with an electrolysis of water somewhere, or acidified sulfuric acid, or acidified water that is. Then air on the other side. You can see several processes, electrolysis, fractional distillation. Then you have ammonia is being produced. So there's Haber process, qualitative analysis, preparation of a certain gas, nitrogen oxide, nitric acid is produced. So a salt, ammonium nitrate. So you can see this one, a very nice flow chart there, covering quite a number of areas. So of course you go ahead and answer the question. Name another source of hydrogen apart from electrolysis, etc., all the way to part E. The very last question, long structured question number 19. Yes, you study the flow chart, you're starting somewhere with the air, you filter again. Like I have said before, this one is for the isolation of nitrogen from the air, the fractional distillation of liquefied air, a Form 1 concept. I've just intentionally brought it here so that it can help you revise. But mainly it has nothing of ammonia in it. However, it has the first step in a Haber process, the obtaining of nitrogen from the air. Otherwise, thank you so much, my students. Keep coming back. Keep contacting me through my WhatsApp number, because in most of my videos I have attached my WhatsApp number. You can be able to revisit and even call me, maybe get in touch with me. Thank you.